Imagine that you're like Tycho Brahe, right? Or Johannes Kepler, or whoever, right? Those people who first did all the stuff about orbits, studied the orbits of planets and the heliocentric model, and how maybe the geocentric theory was just incorrect, right? And you're wondering if things do orbit the sun, how are their speeds? What are like related to the distance, things like that. And you hear later on that these rules might work for like planets, things like that, right? And yet 400 years later, you find out that galaxies, right? They should basically do the same movements, right? The farther away you get from the center, the slower things move because there's less of a centripetal acceleration pulling on it. Basically, like let's say a planet's orbiting the sun, right? You have the sun in the middle. You have a distance away the Earth is, right? And it's an elliptical orbit, so technically you're using a semi-major axis as your measurement of distance away from the orbiting body. Well, from the body orbiting. No, the orbiting. What? Whatever. Anyways, um, so you're taking the semi-major axis, which is basically just an average of the distance, right? So you just average the minimum and maximum distances of the Earth to the Sun at its closest and farthest points, right? The semi-major axis. And you kind of just use that, right? And the larger that is, the slower the thing is, the slower the orbiting body is. And you kind of like use that in basic physics where it's like v squared over r is a centripetal acceleration, right? It's just an inverse thing. You could see through like what is it? G m1 m2, right? The universal constant m1 m2. Those are just constants on top over r squared, right? In our situation, those are the top is constant and the bottom is what varies, right? So 1 over r squared is a relationship, let's say, right? Um, so the larger the distance, the lower the acceleration is, the lower the gravitational attraction is between the two things, right? So the slower the orbiting body is, or has to be to stay in orbit, right? Anyways, I kind of just veered off there. Um, yeah. So right, you have that situation, and it all makes sense. And then you look at a larger scale, I guess. You see because you learn later on, right? Natural progression of things. Planets. The moon orbits a planet. The Earth, let's say, the Earth orbits the sun. And what does the sun orbit? It orbits the center of mass of the galaxy it's within, right? Which we would say is around the supermassive black hole in the center of the galaxy, right? The Sagittarius, whatever it's called, I forget. A lot of terms. I'm not very good at remembering terms. Um, yeah, right? So you naturally expect that Kepler's laws would apply to that kind of thing, right? That standard Newtonian principles should apply. But then like as far back as the early 1900s, late 1800s, scientists, astrophysicists found that for some reason it seems like the universe is full of some kind of matter, right? Like a bunch of mass that we can't see, and somehow it's affecting our surroundings, right? Like I think I read about this. Like there was this one uh, astronomer, Lord Kelvin, or physicist, astrophysicist, Lord Kelvin, from like Britain or something like that. I don't know. And he proposed that there would have to be like thousands of millions of stars that just don't exist because of the way that the velocities of the stars around the sun, right, just started acting, right, and it just didn't seem normal to him, which is why he thought there was maybe like some obscured amount of stars that just aren't visible. Maybe there was just a bunch of dust in the way nobody could see them, right? Um, and I think later on it was like a French term that they used to coin the name dark matter. It was like a French thing, somewhere, something like that. Um, and so from there, like throughout the 1900s, I guess the early 1900s, like because later on, the late 1900s, where it kind of it is shown that somehow there's something that exists out there, right? Some kind of mass that is acting on the rest of the universe, and yet we can't see it or observe it or do any tests on it because it's just not touchable. It's like something in a completely different realm of existence than we could think of, and yet it's there, which is kind of crazy in and of itself. Um, and so physicists for the next few decades they hypothesized the existence of dark matter, right? People would observe the way that our galactic plane and the local neighborhood, the local galactic neighborhood we have, how they would um, move, how the stars would move within them, right, around the center of the galaxy, and it people like scientists kept finding that there was there should be much more mass than there really is out of the stars and the planets that make up those galaxies, mainly the stars, because the planets are like minute compared to them. Like uh, over a million Earths or something like that could fit into the sun, or yeah, much more than a million. Um, so really, it's just the stars and the black holes and all that stuff that are making up the true mass of the galaxy. Um, and the giant gas field. Anyways, um, so so physicists just kept seeing, right, this effect that the gravity effect from like the visible galaxies should be just far too small to allow for the fast orbits of the stars, right, that are surrounding the galaxy that are within the galaxy. And so there should be some kind of measure of mass, right, distributed across the galaxy that should be providing more gravity for the speeding up of the stars in that outer disk of the galaxy, right? And you can't just add more mass into the center of the galaxy because what that would do is just speed up the it would just speed up the stars all together, right? So all of the ones in the inner disk and the outer disk would all speed up together accordingly, right? Or something like that. I mean, hypothetically. So this mass can't just be in the center of that galaxy. It needs to be distributed across the entirety, right? To allow for a uniform distribution of the velocities of the stars. Otherwise, it would just be a continuation of the effect, except with a bigger hypothetical, like theoretical black hole in the middle. Um, and so later on, we developed better ways, I guess, of being able to measure the amount of matter that should be quote unquote dark, right? Through the use of galactic rotation curves, which is basically observing the what is it? I think it's like the distribution of velocities according to distance. I think that's what the rotation curve is. So you could kind of think of it as like the bottom, I guess, an x-axis of the distance, right, is like the plane of the galaxy, like horizontally. So think of the origin being like the center of the galaxy. So let's say that center black hole. And the farther out you go, what is it? You're going out towards the uh, what are the words? Oh my god. I'm blinking. Like the not the crust, not crest. No, I think it's a completely different word. I don't know. The disk, let's say. So you're going from like the inner to the outer disk as the distance goes on, right? And let's say the y chart, the y-axis part of this chart would be velocity, right? So that's kind of what the rotation curve should be. Um, and so you plot those velocities and the distances, right, for the stars, the orbiting bodies around the center, and what was supposed to happen, right, if dark matter or whatever kind of the other theories I'll get into a bit, if those things didn't exist, right, then the plot should be a very large spike upwards, right, and a very small amount of distance near to the inner disk, right? And then it should steadily just decline and drop off until when you get to a very large distance away, the velocity should be nearing to zero, right? So it's just a basically not a very steep hill, but it's very um, very noticeable, right? The effect is very noticeable of the drop off of like the decrease in acceleration, decrease in the force between the center and the orbiting body. But when physicists would plot the actual galactic rotation curves based on data and analysis observation, um, it was found continually that what really happened is that initial spike of velocity with distance, and then instead of dropping off immediately, it just keeps going straight. There's a few bumps in there, right? A few anomalies, and honestly, I don't even know why that is, but I guess I could look into that later. I might just do another um, episode on dark matter because I feel like this is definitely not encompassing everything about it at all. I kind of just wanted this to be like an introductory video. I mean, it is the first video. I didn't feel like doing just like one intro video that would list out the entire channel expectations or whatever. I felt like it would be better just go into the science of things because that's just what I like to do. I don't like to just sit here and explain. I want to get into the grit of the science. Anyways, um, so yeah, it's kind of weird to a lot of physicists why this is happening, right? And so if Kepler's laws aren't working and Newtonian physics aren't working on this kind of thing, then there must be some other reason, right? Something that physicists just haven't known for the past 300 years that it's been developing 400 years. And so later on, right, in the 1960s, more radio astronomy observations that just displayed more evidence that these galaxies were spinning too fast in the outer regions, um, showing something was creating gravitational pull needed to keep these stars in orbit. Um, right, because if they were going too fast and the acceleration towards the center was not large enough, right, because there's enough gravitational attraction, then these stars would just fly off. And so we were just confused. Why aren't they just flying off? Why are they just staying there? Um, then like the 1970s come in, and it's just even more evidence using observation of edge-on spiral galaxies, right? Because it's easier to kind of get those measurements if we're just looking at them directly with spectrographs edge-on, instead of just looking at like the like let's say from our observation point, we could just see that tiny horizontal sliver. So a lot of these efforts were kind of just culminating in more and more evidence that there must be some type of subatomic particle, right? That's um, truly doing all the work in causing these like the cases of gravitational lensing of what is it and anisotropes anisotropes in like the CMB and stuff, the cosmic microwave background. right? All of these little irregularities that shouldn't occur with like a Keplerian physics, Newtonian physics, stuff like that. And so a lot of this was just more work for the particle physicists to kind of figure out. Really just a lot of like pouring of evidence that something must exist. And so dark matter became like one of the most popular, what's it called? Most popular theories for a lot of physicists, a lot of just people everywhere. It's kind of been like sensationalized, especially in like science movies and the media, stuff like that. 'Cause it kind of is just like a very cool kind of fact. It's very fun to kind of think about, I guess I could say, um, because it kind of just proves that there's still a lot more to learn, and we definitely haven't learned everything, and physics is always kind of developing, and we're always going to have to kind of push through another problem that this time we just can't actually see. We can't really observe it, so it's definitely a bit of a larger problem than what past physicists have had to kind of deal with. I guess like let's say what Kepler and Newton had to deal with. Maybe I don't actually know too much about them. Maybe I should also read a bit more about them. Um, Talk about them a bit more. Um, but yeah, I mean, like not being able to observe the the object in study is it's quite a difficult thing to do when you're trying to unlock a new part of your field, right? It's kind of some ways that people actually study the effects of dark matter and if it truly exists and kind of develop theories on it is through the galactic rotation curves, velocity dispersions, and galaxy clusters, kind of just galaxy clusters in general, like what you would see in those NASA images, like the gravitational lensing and all that stuff. Um, so I kind of went over galaxy rotation galactic rotation curves. Um, it's kind of just like the arms rotating around the center and how the velocity should drop off, and yet they don't. Kind of points to the fact that there should be a lot of matter, right? Non-luminous. We can't really observe it. It's not really something that we can see with our present instruments, and it's not just like a an issue of it not being in the visible light spectrum, and we can't see with regular telescopes. It's not emitting any kind of light, any kind of electromagnetic radiation, for us to actually pick up on. And then you have velocity dispersion, which I don't really know too much about. Um, Honestly, I kind of think it's just something to do with the combination a combination of like stars being bound. Well, sometimes stars being bound in systems that obey something called the virial theorem, and together with like the measured velocity distribution, right, the galactic rotation curves, these can be used to like measure the mass distribution in the system in like elliptical galaxies or globular clusters, um, and these don't really match the predicted dispersions from like observed mass distribution, right, the actual mass that we can see. Um, and sometimes they really kind of create complicated distributions of the orbits, and this is kind of like a pretty obvious discrepancy that is used to theorize the existence of dark matter. Um, and then what's kind of cool is that a lot of physicists use like galaxy clusters themselves, just the ones that it's kind of like what you can observe the most, I guess, because you can only observe like there's like a trillion stars in in the Milky Way galaxy, and another trillion in Andromeda, and there's probably quite a few trillion around our little group that we might be able to observe. I don't know how far we can observe individual stars or star clusters, star systems, um, but with actual galaxies, there's so many millions that can be observed in little specks in the sky, right? Little portions of the sky can contain so many galaxies to be able to observe. So it's definitely a pretty important um, way, a pretty important method for dark matter studies. Um, and specifically, their masses can be estimated in a few ways, from like X-rays that are emitted by the hot gas that allows for us to be able to measure the temperature and density of those clusters, giving like pressure and using pressure, density, and temperature, you're able to kind of determine the mass profile of a cluster, right? And then you have gravitational lensing from galaxy clusters, right? Basically, there's some very huge, massive object in the way of something, and it's distorting the light that is passing over it, under it, around it, right? It's distorting it. It's manipulating the electromagnetic radiation coming off all those photons, whatever the waves, light waves, whatever you want to call it. It's just distorting them as they come from the source to um, the area of observation, right? So maybe let's say there's like a huge supermassive black hole right in between you and a source, and then the source is emitting light. You might see that light bending around the black hole, right, and coming to the observation post, right? And what would happen is there would be multiple um, duplicate images of that source around that area where the black hole is, because all of those photons that are emitted, let's say, to the right and left and the to the top and bottom of the black hole, right? They're all being pulled back around by the black hole and then towards the area of observation, right, to our eyes with the telescopes or whatever. And so that's kind of gravitational lensing. Um, and that kind of gives us the ability to measure cluster masses without actually using dynamics like velocity and stuff like that, which is definitely a lot easier, a lot simpler. Um, I think that's it, really. And these methods are really the main ways that we've been able to like agree that whatever matter is there, right? Let's say that dark matter, right? That stuff that is um, allowing for greater gravitational attraction towards the center. Approximately, it outweighs visible matter by like a factor of five, like a ratio of 5 to 1. So 5 times more dark matter in the universe than actual matter you can see, which is kind of crazy when you think about how much matter there is in the universe, but also a lot of the universe is just empty, right? Because there might be a lot of specks in the sky of light, right? Millions and trillions of them, but then you think about like the areas in between, and you think about the like trillions, quadrillions, whatever, huge numbers of miles of light years of distance between them that are just filled with nothing. Maybe a few rogue planets, some dust, but really nothing. So there's actually matter there, maybe. So our universe is definitely not as empty as it could be. So you have ordinary matter, right? And you can kind of think of it as being made up of quarks, protons, electrons, neutrons, molecules, right? Atoms, all that stuff, going all the way up to stars, galaxies, everything right, like that, right? It's stuff that we can kind of feel, think about. Can't do that with dark matter. Um, but a special thing about ordinary matter is that, like in the early universe, I guess, it was ionized, right? Heavily ionized. It was bajillions of degrees or whatever, so the Kelvin in the universe, and it interacted strongly with radiation via something called Thomson scattering, um, which is like the scattering of electromagnetic radiation, right? So what you think of as X-rays, infrared, all that stuff, that's electromagnetic radiation, part of the light spectrum. Um, yeah, so it's the scattering of that radiation by a free charged particle. Um, and it's the low energy limit of Compton scattering, which is something else. Um, yeah, and so it's basically just like a scattering of electromagnetic radiation. But yeah, so dark matter, what's different about it, right? Is that it doesn't interact directly with radiation, right? But what's weird is that it does affect the cosmic microwave background, right? The CMB, with its gravitational potential, right? And by that I mean, like, you know how dark matter is supposed to um, affect the orbits of those stars around the galaxy, right? It's adding gravitational energy to the system. Um, it's observed, or at least theorized. I'm not fully sure, um, but it is shown that dark matter affects the CMB, and mainly on large scales, um, and by its effects on the density and velocity of ordinary matter, right? As in, like, affects the CMB by its gravitational potential and its effects on the density and velocity of ordinary matter, right? So the things that we can observe. Um, and so both of them, right? It's like, although they're both interacting with the CMB, um, the ordinary and dark matter, they kind of like evolved differently with time, and they left different kind of marks on the CMB itself, right? So that the thing that I was saying before, the what is it called, an anisotropy, yeah, an anisotropy, right? Those patterns, um, which is basically just like the property of something that allows it to change, or like assume, I think that's the right word, or assume like different properties, right? That's kind of what anisotropy is, right? So it's like flexing, you could kind of think of it as like the flexing of the CMB in different areas, like creating low density areas, high density areas of background radiation, um, right? Yeah. Um, so like the CMB is a almost nearly perfect black body, right? So it's like a perfect crater observer, or absorber of electromagnetic radiation, right? Light. That's kind of why it's like a black body. Like, if you think about how when you go outside, right, and it's very sunny or something like that, and you wear a black shirt, instead of like a white shirt, the black shirt will absorb much more light, while the white shirt will scatter more light away from it, right? So we call things that are able to absorb a lot of light or interact very strongly with light like that, black bodies, right? And the more perfect one is, I guess, like the more uniform, I think, the body should be, or something like that. I think I butchered that, but anyways, um, so even though it's very close to being a black body, a perfect black body, it still contains some of those small temperature differences, the anisotropies, the fluctuations, I guess, of like of what is it? I think it's like a few parts per 100,000, something like that. Pretty small, right? It's kind of like that measurement of ppm, parts per million, but it's parts per 100,000.